It's not bad. Let me check this side. Oh. I think it's in ọba ò ní pẹ́ lílo ètò ọkọ̀ fún àṣẹ́bẹ̀rẹ̀ nígbà ìbá lílo ètò ọkọ̀ ìwà ní ìgbà ìnáwó ọmọ yẹn pọ̀ lórí ọ̀la mo sọ fún un bọ̀ ń ní máyà ti lílo bẹ̀ tán àwọn ọmọ torí àwọn ọmọ ṣe ń bọ̀ bí òun lọ ilẹ̀ tí ó lè dájú. Just give me a few minutes, I want to connect this. So good morning everybody. I hope we slept well. No, Hassan. We slept well now. I believe you are estimating already. Trying to access this. Hello, can we hear me? Those who are watching online. If you can hear me, let me see your comment, please. You can try and share the link to your friends. I'm also trying to copy and share now. Okay. So we are starting in the next few minutes. Okay, all right. Kindly share the link among your friends. How is this thing not coming now? Can you hear me? Okay. Let me push it forward. Somebody should send this one to slide to this number because it's on this phone. Tell them to send it if you have it. Electricity slide. There are some slides that there is a link that contains everything in one PDF. But if you have for electricity alone or for everything, just send it here. Good morning. Good morning.
So we are here for the UC.
I think F2 too. We are starting soon. Just a few minutes. Network is good now. This thing will be usually I can send the link to the channel. You didn't deliver on the group, but you don't deliver on the channel. Oh yeah, now let's start. So we are starting with particle physics. Without wasting much of our time. We will soon leave here, so don't mind the noise for now. This is just temporary. As we all know, okay, let me introduce myself. We all know me. My name is BelloᵈÇᵈ. The one usually called Tutor Belloᵈچھᵈ. So this is my faculty. I'm in Science and Technology Education, and I'm studying Education Physics. So nice meeting you. If I have not seen you before. So alright, particle physics. So without wasting much of our time, let's start with elementary particles. Like we said, we have 17 elementary particles. We've done all this, so we won't be wasting much of our time. And they are subdivided into two, which are what? Fermions and what? And leptons, isn't it? And this guy too is subdivided into what? Fermion and boson, sorry. fermion and boson. Why this one is subdivided into what? Quarks, right? Quarks and what? And leptons. So this guy is subdivided into what? 6. We have the UCT and we have the what? BDS. Bachelor of Dental Studies. So all this UCT, they have a charge of what? Plus 2 over 3 E. While all the BDS, they have a charge of what? Minus 1 over 3 what? E. U stand for up quark, this is sham quark, this is what? Top. This is bottom. What's another name for bottom quark? Beauty. What's another name for, I think there is one too. Strange. Which one? What are you saying? Top or truth, yeah. So all these ones, they have just one name. Up, sham, this top or truth. Because they can give another name that day. So if you don't know the other name, you won't know what they are talking about. So you just think they are asking what they are not talking. It's in the slide. So up quark, sham quark, top quark or truth quark, bottom or beauty, down quark and strange. So for leptons, we have what? We have electron, we have muon, we have tau, we have, and they are neutrino. We have the electron neutrino, we have muon neutrino. What's happening to this marker? I have ink here, sha. We have muon neutrino. Is that the correct spelling? We have the tau neutrino. So the charges of these are what? Minus E, right? Minus E. Why all the neutrino are what? The 0, 0, 0. There's a question I want to ask. What's the difference between chargeless and neutral? What's the difference? When they say a particle is chargeless and when they say a particle is neutral. Or let me ask this way. The neutron in the nucleus of an atom, is it chargeless or neutral? It's neutral. The neutron in the nucleus of an atom, is it chargeless or neutral? How many of us speak neutral? How many of us speak chargeless? Let's talk now. Is neutron chargeless or neutral? Like the boat. To raise your hand. How many of us speak neutral? Yeah, can we justify that? How many of us speak chargeless? Now, normally in the normal secondary school terms, it is chargeless. But in physics 102, it is neutral. You know, in secondary school, they did not teach you anything about quark. So it's like neutron is not subdivided. For secondary school level, neutron is not subdivided. Am I right? You only have 3 things inside the atom: the proton, the neutron, and the electron. But in physics 102, you have more than 3 things because inside all those proton, neutron, you still have quark. So if you are regarding to quark, this guy is not chargeless, it's neutral because quark has charge. Neutron contains 3 quarks. UDD. Isn't it? Up, down. These 3, they have charges. So, but because the charges cancel out, that's why neutron is neutral. But it is chargeless. Am I making sense? Because there are charges inside. But because they cancel out, so it's neutral. But for the secondary school level, it's chargeless. Because you can't teach those guys quark. They are brain with things. So that's that for that. What of so like the one we all also know, if we say okay, maybe when we get there, sha. Now for bosons, we have 5 bosons, right? And 4 of them are what? 4 of them are what? Is it gauge or Higgs? 4 of them are gauge, right? And we have what? The Higgs boson. And this gauge, I hope everything is showing, sha. Yes. Okay. You'll be managing to a swap class. Nobody is even not come physically. So we have gauge boson. No, this thing we are just playing. We have not gotten to today's deal. Gauge and Higgs. So we are just doing revision now. So gauge is subdivided into 4. Which are what? They are what? They are photon. They are gluon. They are W. can be either W plus or W minus. And we also have what? Gluton. Gravity. No. Z boson, thank you. Now, one thing about gravity is that it's theoretical. Are we together? And throughout your past questions, it's not asking anything about gravity. It's just in the slide to show you that there is something else called gravity. It's not actually, these are the main 5 bosons that makes this elementary particle to be 17. Why they mention gravity here is that if we have, now for photon now, this is the reason why gravity exists, For photon is a carrier of electromagnetic force. Am I right? And Z boson and W boson, they are carrier of weak forces. Are we together? Gluon is carrier of strong nuclear forces. Are we together? So, we also have what we call gravitational force. We have gravitational force. So, but there is no practical evidence that we have a carrier of gravitational force. But theoretically, if there is this gravitational force, then there should exist a particle that carries it. So the particle is what we call gravity. Are we together? But it's not yet discovered. Am I communicating? So that's why it's not, but they just mention it there to tell you that, okay, as far as science is concerned, the history of science, there is something called gravity, theoretically, but it's not yet discovered. So we assume that this gravity is a carrier of gravitational force. But nevertheless, when they are mentioning 17 particles, elementary particles, it's not included. Because we can't see it yet, it's not discovered. So we don't even know whether the particle exists or not. Am I communicating? So those are the 17 elementary particles that we have. So now we move to, and there is this something in the slide, a guy and a lady enter my DM of them saying they don't understand. And I had to write a note on it, but I will still feel like let me go back to it again. There's a place in the slide that says something like I want to quote it exactly as the slide put it. They are trying to say the charge of a macro, or is it macro or micro? Okay, macro rather. The charge of a macroscopic object is very, very small compared to its total charge. Do you remember that statement in the slide? And it said the charge of macroscopic object, that is all the everyday object that we are seeing, like this bottle now, or whatever, the charge of that object is very, very small compared to the total charge of the object. Now, the charge they mean here is that the slide should have said the net charge. They're actually referring to the net charge, and I think I described it enough in that note. They said the charge of that object is very, very small. I think they said about 10 raised power minus 12 of the total charge of the object. So that charge they mentioned there, they are referring to net charge. For instance, let's take chlorine for instance. Chlorine has Cl, let's say chlorine atom now, neutral chlorine, not the ionic, not the ion one. Chlorine has, what's the total charge of chlorine? Total charge now. Oh, sorry. What's the total number of proton to electron? Chlorine has how many protons? Number 17, are you sure it's 17? I can't remember again. What of the electron too? 17. That is if it's neutral, right? So now, assuming we now have chlorine ion, maybe when we disturb the stability of chlorine, it becomes an ion. So what happens to proton number? It stays the same, right? What happens to electron number? Is it reduced or increased? We have 18. So now, what's the net charge of this chlorine now? Minus 1, have you? So this net charge is very, very small compared to this 17 plus 17 or this 18 plus 17. That's what that slide is saying. Am I communicating? This net charge, normally, if you want to say, they are using everyday language for that statement in the slide. They use our everyday language in the sense that it's uncommon to say what's the net charge of chlorine, isn't it? What we normally say is that what's the charge of chlorine, am I right? Because what's the charge of calcium? Immediately you say plus 2, isn't it? And you are actually referring to the net charge. Is that not so? So what they are meaning there is the net charge. That is the net charge of an object is very small compared to the total charge inside the object. So that's just what the statement is trying to say. So now, And don't forget we have mass of electron, we have mass of proton, and we have mass of neutron. That's everything in the atom. They also have mass. All the particles like the electron, the three subdivisions, the proton and the neutron. So who can tell me the order of the increasing mass of electron to proton and to neutron? Which one have the highest mass? Which one have the lowest mass? The least mass rather. Electron is highest.
No, it's the smallest.
The smallest. What's the value? 9.1 times what? 31 kg. What of proton?
1.67
Times 10 raised by what? Neutron 1.6 something 2, abi? But which one is all these will be approximately equal, but which one is bigger? Proton or neutron? Neutron, abi? So we can conclude that Me, let's say Me far less than. You say neutron is bigger than proton, isn't it? Far less than MP, less than what? Mn. Or you say Mn greater than MP, far greater than what? Me. When you see double sign like this, it means far greater. It's about 1,000 times greater than. These two are about 1,000 times greater than this, so it's far enough to be represented with a double symbol. Now, this board is actually bad. When we swap to the other class, everything will be better. So now let's move to the fundamental forces. My main focus for today is Coulomb's law and electric field with dipole. So this one let's just have some fun. Fundamental forces. So how many do we have? We have 4. We have the strong nuclear force. We also have what? The weak force. We have the EMF, electromagnetic force. And what? Gravitational force. Gravitational, yeah. So what is the relativity strength? That is the relativity of the other forces to strong force. Weak force is compared to strong force in terms of strength. With what standard? What can I put it now? With what? All these 10 raised power something. That's what I'm going to say. I don't see the correct thing.
21 years students.
Okay, let's first write the order. There is something we call C wedge, Am I right? So this is the order. So if I don't remember, this is just what I try to remember. Okay, let me just put it this way. So here we have strong. Then okay, it's arranged already.
Yes.
This is the order of what? Decreasing strength. The C wedge is the order of decreasing strength. So if they should swap it, that's order of increasing strength. So this one compared to this, if I don't remember, I used to code it like a 23-year-old guy scored 3, I think, yeah, a 21 rather, scored 338 in jam. Yeah. So this one is 10 raised power minus 2. Then this one is 10 raised power minus 13. This one is 10 raised power minus 38. So now, compared to strong force, weak force is about 10 raised power minus 2 least in strength or lesser in strength than strong force. Electromagnetic force is about 10 raised power minus 13 lesser in strength than strong force. Gravitational force is about 10 raised power minus 38 lesser in strength than strong force. Everything they are related to strong force, not this to this, but they can also ask what is the relativity in strength of gravitational force to electromagnetic force. What's the answer? If you are comparing the strength of this based on power, based on standard power like this, compare gravitational to electromagnetic, what would be your answer? Just 38 minus 13 now. Isn't it?
Yes.
And that gives you what? So this is the answer. 25, sorry. So that means gravitational force is 10 raised to power minus 25, lesser in strength than what? Electromagnetic force. So I think there is something more to say about that. I'm not done with that aspect, sorry. So there is something I heard of recent and it's going viral among some students. Someone came to my DM, said they were told that the force between proton is EMF. You are part of those who were told. Can I see on the force between proton to proton, like inside the atom of an element. You know we have proton. Let's for instance, let's take oxygen for instance. You know oxygen has how many protons? 8, right? So inside the nucleus of the atom of oxygen, let's say all the protons that are there. So I heard that they are bound together by electromagnetic force. That's not partially wrong. That's completely wrong. How can electromagnetic force band protons together? And this is the reason. Now let's start from. Now the person justifies his answer by saying inside the proton. We know inside the proton we have 3 quarks, right? We have the up, and what? And they are bound together by what? Gluon, right? And gluon is a carrier of strong nuclear force. So at the same time, you can say they are bound together by strong nuclear force. Am I right? Now, because inside the proton, all the quarks are bound together by strong nuclear force. So the person think proton also should not be bound together by strong nuclear force, since inside is already bounded together by strong nuclear force. I get what I'm saying? Which is very wrong. Even proton to proton, they are bound together by strong nuclear force. Why can it never be EMF? Because EMF can either be a force of attraction or repulsion. And proton, they are like charges. So if the EMF is attraction, how can I put it? If the EMF is repulsion, so it has to push the proton away, which means they can't stay inside the nucleus. But we still have proton inside the nucleus, which means EMF is not applicable for the force that binds proton to proton together inside the nucleus. There's only strong nuclear force that can overcome the repulsion between proton and proton. No, they are like charges. It is only this SNF that can overcome the the force of repulsion between them to join them together. EMF can never. So if you see that EMF contribute to the repulsion, am I communicating? So of which we have never had before, unless when we are talking of radioactivity. And don't forget, till you finish this course, proton is not disturbed. I hope you remember. Proton remain intact. So since you are still under physics 102, it can never be EMF, because what happens to EMF? It will push the proton away from each other, and there is nothing like that in electricity. So it's strong nuclear force. Whether the quark in the proton or proton to proton in the nucleus, strong nuclear force keep bind them together. So that's that for that. Those are the little questions they can ask you. And there is what we call the law of conservation of charges, which state that what? Charges can what? Can neither be created nor what? Not destroyed. But can be what? Can be transferred from one body to another. If charges can neither be created nor destroyed, then how then do we? Before then. Charges can neither be created nor destroyed, but can be transferred from one body to another, says the law of conservation of charges. But we can't create charges, but we can create charged particles. Now, my question is, what's the difference between charge and charged particle? What's the difference between charge and charged particle? You can't create charge, neither can you destroy it, but you can create this guy, and at the same time, you may destroy it. So what's the difference between these two? Charge and charged particle. Anybody? No. Let's talk now. What's the difference between charge and charged particle? It's just simple English. I say, what's the difference between Bellow and Bellow's biro? Don't you know the difference? And what's the difference between charge and charged particle?
Electric charges. Why charges are properties associated with electricity?
So charges, in a nutshell, charges are the charges are the possession. Charges are the should I put it that way? I'm coming. Let me look for a better English. Okay, let me ask this way. Charge, I think it will be better this way. And charged particle. which one is smaller? Charge and charge particle, which one is smaller? How many of us pick this? How many of us pick this? Charge and charge particle, which one is smaller? Charge particle, which one is the answer? It will make us to define this thing very well. Charge particle, which one is smaller? Okay, how many of us pick charge? How many of us pick charge particle? Which one is smaller? No, dental surgery, I'm asking you. Which one is smaller, charge and charge particle?
Charge particle.
Oh yeah, which one is smaller? Now, like we said, this guy is smaller than this. Am I communicating? Okay. Am I smaller than my biro? Even though it's house, I'm still bigger than my house. Even though, if this is my room, I'm bigger than it. In stature, it may be bigger than me, but I'm big because I can demolish it any day. I have the power of it. So this guy is smaller because this is charge, and this particle is one of the property of that charge. Like charge. Let me even put something here so that you know what you are talking about. Are we together? Charge particle. That is, whatever particle it is, it belongs to that charge. So actually that charge overcomes the particle. So this guy is smaller and this guy is bigger. So we cannot create this guy, but we can create a particle in a charge. Are we together?
Yes.
Do we get what I'm saying? Yes. We cannot create this guy. Like you cannot create or destroy more charges. But inside those charges, you can disturb its particle. You can have some particle inside those charges. The difference is that I'm looking for a better way to put it. Let's say, we have elementary particle, isn't it? We have elementary particle like let's say quark. Let's say quark, an up quark to be precise. This is a particle, and it has what? Plus what? 2/3, right? Now, there is nothing you can do to this guy that will not make it 2/3. There is nothing like you cannot add to this charge. You cannot remove from it. But let me not make this thing confusing. I'm looking for a better way. But you can let's just say I'm coming with. Okay, like I was saying, you cannot remove from this, neither can you add to it. But you can have more quarks, yeah. And you can remove, let's say we have proton. Let's even assume we are dealing with radioactivity. Okay, let's not go that way. I'm looking for a particle that can be splitted. Let's say we have pion. A pion contains what? A quark and anti-quark, right? This will even be better now. I'm so sorry. I'm looking for a way to maybe we should just move on without wasting much of our time. But I will surely find a better way to explain that. Now, but for now, you cannot create this guy, but you can create this guy. Okay, I think I find something to say. I'm coming in. Charge. Okay. Let's not enter confusion. Just know for now. Before we are done, I will find a better way to explain that. You cannot create charge, but you can create charge particle. And how do we create this charge particle? By what? Disturbing what? By disturbing the neutrality, or what we call the stability of an atom. And when we disturb the neutrality of an atom, that is when we have atom becoming ion, whether minus whether negative ion or positive ion, like aluminium 3 plus, or in a nutshell, I'm looking for a way to still explain this. I don't want to leave it. See, all these charges, I'm coming now. Okay, don't worry, that we get it. So, by disturbing the stability of an atom, you can have all these ions, this and this. So that's when you have the neutrality of an atom not to be neutral anymore, because the stability of that atom is being disturbed. And that's the difference between creating charge, which is not possible, and creating charge particles. We are still coming back to this part. There is a kind of analogy I'm looking for to break it down. But I don't want to waste much of our time. Let's just move on to the next thing. So before we go to the main deal, I'm not with the slides, so I don't even know what's next. But let me just go. What should be next in the slide? And one thing you also know, charge, you must know, charge can never exist without a body. Are we together? But a body can exist without charge. When we get to question, the question are not asked directly like this, but when we get to questions that are related to this, you will see it, and I pray that you'll be able to answer it. So the next thing I also want you to know, there's a question I saw of recent, before I move to the...
Yeah, so you guys are still interested in this question.
Yeah, should we still stay?
But I feel like this place is better because the bodies.
It's just the body. Let's stay here first, when others are coming.
Class increases.
Yeah. So now, there's a question I think, I sent of recent. They said, and I want to, I think it's from the slide, but you will not see it in the slide, but it's inside the slide. The question is like this: electricity I'm coming. I'm looking for a way. Okay, let me check it. Oh, I'm using my phone here. Electricity is as the result of presence of charges or presence of charge. Then we have let me remember those English. Okay. I'm coming up. Okay. Moving charge and stationary charge. Moving charge and stationary charge. Then we have electrostatic and electrodynamics, respectively. Is this definition true or false?
It's false.
Well, you have seen it before. Is the definition true or false?
It's false.
Okay. Electricity is as a result of presence of charge. Moving charge, that's also present. Stationary charge is present. Electrostatic means static charge, present. Electrodynamic means moving charge, present. Is that not true? So how is it false? Because we still do many questions that are related to these terms, so that you understand how to answer them. That's why I think the question is from PhD. So how is it false? Can you just justify your answer?
Moving charge is electrodynamic.
Like, we are dealing with English here now, not easy to
Yes. Respective the means
So what's the meaning of this guy?
consecutively.
Moving charge is
For electrostatic, is for electrodynamic, and stationary is for electrostatic. So you missed the other.
I'm coming though. I'll give you another one very soon. Don't worry. So now, this word respectively here, you see all these things? You see all these semicolon, comma, they are meaningful. Now you see the word respectively here, is saying these two respectively are related to the order you put here. Are we together? Yes. Now your definition here is that electricity is as the result of presence of charge. Now semicolon. The meaning of this semicolon is that you are telling us more about the presence of charge. Like this definition is not stopped here. Are we together? This definition is not stopped here. So you now want to expatiate on the presence of charge. And your expatiation is now saying the presence of charge are what? Moving charge and what? Stationary charge. So this is where the definition stops. But there is a comma, not full stop here. So now say, respectively with what you are saying before, then you have electrostatic, you bastardize everything already. Because respectively to what you just said, the first thing that should appear here should be electrodynamics. Are we together? Because why? You have moving charges first. Do you get what I'm saying? So this one is not even physics, it's just your English. So please take note of that. And all those, I think it's only Prof. that I used to ask for possibly. It's like 102 also asked. Yeah, 102, I think he asked. But it's mainly from Prof. All those possibly for certain things. I struggled with that for like weeks. No, it's simple to you now, fine, no problem. But then it was not fair. I used to miss everything about possibly true, possibly false. So now let's move to Coulomb's law. There are still something to discuss under this particle physics. We are still coming back to that. I'm just trying to beat my time. But my main focus today are all those calculations and the directions, particularly those directions. Coulomb's law. Now, like I said, when I was teaching on Telegram, the definition they gave me in secondary school, I know the definition in all those textbooks they are around. And they are not complete, rather. So let's say, who can define Coulomb's law for me before I proceed? Coulomb's law is defined as what? First of all, if you say Coulomb's law is defined as the force of, it's even not complete. I think there is a word that is missing there. I don't even think that part is even in the slide. Coulomb's law can be defined as the electrostatic force, not just force. Coulomb's law is not talking about electrodynamic force. Are we together? Coulomb's law is defined as the electrostatic force of attraction or repulsion. So these are the things that are missing in those definitions. This, so, and these two. Just say it's the force between two. So you have to specify. You have to dictate the two because it could be an attractive force, it could be a repulsive force. Unlike gravitational force, that one is only a force of what? Attraction. It's not repulsion, it's always attraction. That every object in the universe attracts each other with a force directly proportional to the product of their mass or whatever. So electrostatic force of attraction or repulsion between 2 point charges. Between two charges, Q1, Q2, as labeled, or Q3, Q2, anyone. Force of attraction between, electrostatic force of attraction between two. What am I saying?
The product of
I'm coming. Is the, wait. Coulomb's law state that the electrostatic force of attraction or repulsion between two charges is directly proportional to the product of the charges and what? Inversely proportional to the square of the distance between them. And yet, that's not even complete. Sorry. The completion is that it's directly proportional to the magnitude of the product of the charges. There must be magnitude here. So, which says the force is what? Directly proportional to what? Q1, Q2 over what? Over R squared. Are we together? Your distance cannot be negative, even though it can be on the negative axis, but you're only picking the unit. So if you like put the absolute value on everything, all this stuff, it does not affect. Do you get what I'm saying? If I put my distance on the negative y, I'm still picking the distance between here, which is 3, not minus 3. So at the end of the day, I can now be dictating the direction based on the axis it lies on. Are we together? So now that's why this one does not need the absolute value because it remains positive forever. So now F is directly proportional to magnitude of Q1, Q2 over what? Over R squared. That is F equals to what? K Q1, Q2 over what? Over R squared. Where K equals to what? 8.98 times what? Newton per meter square per coulomb square. And don't forget, they are different. They asked last year, they asked last 2 or last 3 years. Both of them are not the same. One is for speed of light, while one is for charge. I don't know why on earth they will be tricky students with this. They will be tricky students with this. But the reason why it's like that, the reason why you will always fall into that trap, but now that you have known, we thank God, is because your answer in the option, the only answer in the option will be the one that will carry this sign. So your mind will just, since I can see my answer, but you won't check the sign. Same thing happened to many. I think I was not told that I would have picked. For like the question they asked, what is the charge of helium? They can ask in 2 ways. Charge of helium atom and helium nucleus. Note this one now is nucleus. Nucleus only contains proton and neutron has no charge. Yeah. So it's only the proton that we are calculating here, which is 2 times what? 1.6 times 10 raised power minus 19. So this guy will give us 3.2, right? Times 10 raised power minus 19. So this is the only answer that is correct in the option, but they will not put small c. And option E, you will not see none of the above. So your answer should be none of the above, because that small c is for speed of light. So take note of that. So now let's move to those direction stuff now. And I want you to pay a very good attention here, because this part going on, this is bigger than. So these parts are the real matter for today's class, and that dipole too. So before we deal with insulator and conductor, now when we have, and we also have this law that says what's the essence of buying into that? Oh shit. I think I'll just have to. So now, which law say that like charges repel and unlike charges attract?
Fundamental charges.
Which law state that?
Oh.
Which law state this? We know it, but which law state it? That's fundamental law of what?
Of charges.
Let's talk now. Fundamental law of electrostatic. There is fundamental law of electrostatic state that like charges they repel and what? Unlike charges attract. So now if you have positive, now this is where the issue is now. Let's just start. We are just starting now. You have positive and positive charges. You have negative and negative charges. You have positive and negative charges. So where will be the arrow? Just wait, I'm coming here. For number 1, which of those arrows is correct? Which of of the two is correct? So, like, okay, why is this guy not correct? Maybe they are opposing each other now. They are sure opposing each other. But which of these two is correct? Okay, what? Okay, let me put. Now, if it's attraction, which one can I put again? Which one is correct? The first one, I mean. So now the thing is that you can think that since these guys are facing each other, it is likely because if two people are fighting, they actually face each other now. Yes. And when we say repulsion, that is they face each other, like they are fighting each other. But the concentration is based on look here. This guy is repulsing, is pushing this one, right? Isn't it?
Yes, it is. And
this guy is also pushing this one. So this arrow is based on the how can I put it? This arrow here is based on the force of the second charge on the first charge. The arrow that is attached to each charge is based on the force of the other charge on it. For instance, this arrow here is telling us which way this charge is going. And if it's repulsion, can it come like this? Do we get what I'm saying? The arrow here is based on the force exerted by this on this. So it's telling us which way this guy is going. So if you say this is pushing this, it will definitely be going this way. So this is the correct arrow. Am I making sense? If you say this guy is pushing this, then this is definitely going like this. So this is the correct arrow. So when you have like charges, the arrow is like this, not this. Are we together? So same thing happens to this negative. But for this guy is attracting this, right? Yes. So that means this will be coming like this. So this arrow is correct. Isn't it? This one is attracting this, right? That means this guy is coming like this. So this arrow is correct. So whenever you see this, it's attraction. So this is repulsion, and this one is what? It's attraction. I hope that's clear. So now, give me one question under Coulomb's law in the slide. Calculation. One question. I asked someone to send me has anybody sent it? Let me check. If you have seen any question from Coulomb's law, let's quickly do it. We don't have time. Have we seen any? Be reading it first before I'm done. We have the question.
Given 2 point charges, Q1 minus 75.
Q1 equals to what?
Minus 75 nanocoulomb.
Nanocoulomb.
And Q2 plus 25 nanocoulomb.
Q2 equals to plus 25
nanocoulomb. Separated by R equals to 3 centimeters.
What's our Q1? 75. You don't need the minus because we are dealing with magnitude here. Times 10 raised power minus 9. That's nano, right?
Yeah.
What's our Q2?
25 times 75.
Times 10 raised power minus 9. Divide this by 100. The thing is, if you use this theory like that, you will see answer in the option. That's just it. You will always see it there. Because they know that some of you will use it just like the plus or minus 2 meters per second square in that test. So now we have divided this by 100. What do we have? 3 times 10 raised power minus 2. All square. Let's just put our minus 4 direct. Are we together?
9 times.
So this cancel this, right?
It will be 9 times 10 power minus 4. 9 times 10 power minus 4.
9 times 10 power minus 4.
Meanwhile, it's
Okay, sorry. Now if you square it, you will square 3 too. Thank you. So and this This will cancel this, isn't it?
Yes.
So now this guy will go 10. Here we have 75 left times 25 times 10 raised by what? Minus 5. If this one goes up, it becomes positive.
Yes.
So it is subtracted from minus 9 to have this. So here we have this guy. This one turns to 7.5 times 2.5 times 10 raised by what? Minus 3. Is that so? Yeah, I think I'm right. I just remove 1 from this point. So let's just do this. What's the answer? 7.5 times 2.5. 7.5 times 2, 15 times 0.5. That's 18.75, have you? Times what? 10 raised by minus 3. Is that the answer? Have we not made mistake? That's the answer. So this guy now give us what? 1.875 times 10 raised by what? Minus 2 Newton. Now, this is our F12. If you also find F21, we still get the same magnitude, isn't it? But what will now be the difference? Okay, what's the direction of this? Towards where? Now, if you have Q1, Q1 is negative, right?
Yes.
And Q2 is what? Positive. There's a force of attraction. The arrow will be like this, isn't it? So the force exerted by Q1 on Q2 is towards where? The force exerted by Q1 on Q2 is towards where? Towards Q1. Listen, because some people, I'm looking for you. If you say the force exerted by, the one we explained earlier, you have force of attraction between them. And I told you that this arrow is based on the direction that the charge that the arrow is attached to, the direction the charge is going, is for this arrow. Now, this charge is coming to Q1 due to the force exerted on it. So the force exerted by Q1 on Q2, the arrow is this direction, which is facing Q1. So this guy will be what? Towards what? Towards Q1. Now the force exerted by Q2 on Q1, because it's an attraction, so Q1 is coming like this. So that's what? Towards what?
Q2.
Towards Q2. Now everyone can calculate this, even from secondary school. But this is where you can just have issue. But for this question, this one is still nothing. We are still going to something now. So, but before we get to something, do we have another simple question here? We get to something when we enter electric field. That's where all those directions are very, very complicated. But they are still very simple if you understand what you are doing. What's the next question there?
3-point charges.
3-point charges.
Q1 equals to 5 nanocoulomb.
Q1 equals to 5 nanocoulomb.
Q2 equals to 1 nanocoulomb.
1 nanocoulomb.
And Q3 is minus 3 nanocoulomb.
Minus 3 nanocoulomb. I did this video to somebody comment that when we get there, the comment is funny to me. He said, how do we know that this is positive? Wait, let me write it very well so that you will see. How do you know that these two are positive? They need to tell you. This is already negative. Like they don't need to tell you that this is positive. So now let's move on.
Located at 0 centimeter,
0 centimeter,
2 centimeter,
2 centimeter,
and 4 centimeter.
4 centimeter respectively. Now let's go back to that English question I asked earlier. That definition of what's it called? Definition of electricity. That will say moving charges and static charges, electrostatic and respectively. Now look at this guy now. After we are given these 3 charges, we are now given distances, right? Respectively. Now they put respectively. Can you attach 2 centimeter to Q1? No. Can you see what we did earlier now? Can you attach 4 centimeter to Q1? No. Can you attach 0 centimeter to Q3? They have to follow each other. That's the meaning of that respectively. Same thing with what we did earlier when we defined electricity. So Q1 is located at this place. No, they did not have it directly that Q1 is at 0, Q2 is at 2. Did they say that? They said, read the question again.
3-point charges Q1
Uh-huh.
Q2.
They mention all the charges first. Uh-huh.
Minus 3 nanocoulombs are located at 0 seconds.
So they mentioned everything before they gave us this. So it is you that will care them. You cannot say this is for this because of this guy. That is respectively with what they call this order. So this is given to this to this, just like we did earlier then for electricity. Now let's move on.
Calculate the total electric force F23 exerted by Q2 and Q3 on Q1.
F23, like what I told you earlier, exerted by what? Q2 and Q3 on what? On Q1. Now so we need to find them. You can do it directly and just put your addition. That is F23 equals to what? F21 plus what? F31, right? The force exerted by Q2 on Q1, the force exerted by Q3 on Q1. They are telling me to find the force exerted by Q2 and Q3 on Q1. So Q2 on Q1, then Q3 on Q1, you add them together. What will be Q2 on Q1? That's KQ2 Q1 over what? R21 squared. That is distance between Q2 and Q1. Plus what? KQ3 Q1 R31 squared. Are we together? So this one now gives us, since they have the same K, you can bring the guy out. They even have the same Q1. Bring it out. So here we have Q2 plus what? Q3, right? Over what? R21 squared plus what? R31 squared. Are we together? If I minus 9 because it's 1, right? What's Q3? 3 times 10 raised to power minus what? Divided by, what's the distance between Q2 and Q1? 2, just 2, I mean. If you square 2, what do you get? 4 times 10 raised to power minus 1 because we have to convert to meters. Plus, distance between Q3 and Q1 is what? 4. And some people can make mistakes and just say 4 minus 2, 2. Like something like this. Let me even draw it. Here you have Q1, Q2, Q3. 0, 2, and 4. Mistakenly, if you are not careful, mistakenly you can be using the distance between these two. Please just take note. Q3 and Q1 is the distance between the two of them. So which is 4 centimeters. If you square for what do you have? Times 10 raised to power minus 4. You know, if you convert this to meter, you have 10 raised to power minus 2. If you square it, you have 10 raised to power minus 4. So, what happens next? 10 raised to power minus 9 is common to them, have you?
Yeah.
Okay, let me put my 1 here. 1 times 10 raised to power minus 9. I just want to do this, cancel this, right?
Yeah.
9 times 5.
45.
45. So here we have 45
Times 10 per minus
into, what is common to these two?
10 per minus.
Okay, let's bring it out. Times 10 raised to power minus 9. What do you have left inside?
4.
1 plus 3, have you? Which is what?
4.
4. Divided by, this is 4, right?
10 per minus
4 times, what is common to these two?
10 per
10
minus
raised to power minus 4.
20.
Divided into what? 4 plus 16, have you?
Yes.
Like you can just do this thing without calculator.
4 year 1, 4 year 5.
You get what I'm saying? 4 year 1, 4 year 5, have you?
Yes.
5 year 1,
5 year 9.
5 year 9, have you?
Yes.
So if this 10 raised to power 4 goes up, what do you have left?
10 times 10 per minus 5.
I think that's all. Is that? I hope there is nothing left. Is this the answer? I doubt that. The answer doesn't look familiar. Is that the answer?
There's a mistake in that factorization. That has
Don't worry, let's do what we can do. So let's just do it gently. I just want to do it without calculator so that you know on that day.
I was supposed to add the R and the
Let me check. Oh, it's true. Sorry. You cannot have those distance like that. That's the mistake. We can't have these guys. Sorry, we have to. They are not the same. Like even though they are the same or whatever, we are not hard. If they are the same, we just pick one. If they are not the same, we separate them. We can't have them. Thanks for that. So here we have Q2 over R21 square standalone plus what? Q3 over R31 square standalone. Cannot do it like this. See, don't trouble yourself. Just do the normal one we know. Find answer of this. Find answer of this. Add together. You get your. Are we together? So here we have 9 times 10 raised to power 9. What's our Q1? 5 times 10 raised to power minus 9. What's our Q2? 10 raised to power minus 9, have we? Because it's 1. 1 times 10 raised to power minus 9. Over 4 times 10 raised to power minus 4. Plus what's our Q3? 3 times 10 raised to power minus 9. Over what? 16. The distance between Q3 and Q1 is 4. 0.004 meters. So 16 times 10 raised to power minus 4. Are we together? So here, this cancels this. 9 times 5? 45. So this one we have, if this 10 raised to power 4 goes up, this one will become 10 raised to power minus 5, have we? What is 1 over 4? 0.25, have we? Times 10 raised to power minus 5. Just do it the normal way, you understand. You don't get what you are doing. Plus, if this one goes up, it becomes 10 raised to power minus 5, have we?
Yeah.
What is 3 over 16? Can quickly punch that in the CBT calculator, unlike you doing all those standard form. Eh? It's 0.19. That's what?
0.44.
0. What? 44. So, oh yeah, multiply by 45. What do we have?
1948.
Is that the answer? The guy who read the question, what's the answer? Oh, oh yeah, talk now.
2.809 times 10
Why are we not making mistake?
Are we subtracting the 240 so we are adding them?
Go down, baby. Sorry? We are not, it's hard. I have to consider the direction, sorry. So it should be subtraction at the end of the day, I've forgotten. So, that's why this is correct, but it's not ideal. Because it could be subtraction at the end of the day. Do you get what we are saying? Depending on the sign of the charge. So we are actually subtracting these guys. Why? Because the force exerted by Q2 on 1, look at it. Q2 on 1, you know, both charges are like charges, they repel, right?
Yeah.
That means Q2 will be pushing Q1 here. Isn't it? To the negative x. Now the force of Q3 on 1, they attract, isn't it? They are on like charges. That means Q3 will be attracting Q1 to this side. Let's put it here. Are we together? So the total force on Q1 is both repulsion and attraction. So that means as Q2 is pushing it here, Q1 is bringing it back. So the net force on it cannot be addition of both. It will be subtraction. Like the net force. Why? Because it's going here, it's also going here. So the net force is what we are looking for now in the sense of the direction. So we are going to subtract at the end of the day. The subtraction. I hope we know how the subtraction now. Because it's coming like this. The force exerted by Q3 on Q1 is attraction. So Q3 is bringing Q1 to the positive x. But Q2 is pushing Q1 to the negative x. It's like you moving a box. You are pushing it like this with 5 Newton. And somebody is pushing it back with 3 Newton. The net force on the box is 2. 5 minus 3. So the net force, the total force on this guy, the net force is, I don't know whether it's going there at last or coming here. We know now. Later on. How do we know? So I'll just prefer we do it separately so that everything can be clear. We have to check which one is bigger. It should be this. 0.25 is bigger than this. But let's do it separately so that Q1 is what? 5 times 10 raised to power 9. Q2 is what? 1 times 10 raised to power minus 9 rather. Divided by 4 times 10 raised to power minus 4. What's the answer? This cancel. 9 times 5 times 1. 45, Abi. Times 10 raised to power minus 9 divided by what? 4 times 10 raised to power minus 4. So this becomes 45 over 4 times, if this one goes up, it becomes plus 4. 10 raised power minus 5. What's 45 over 4?
11.25.
So our F21 equals to what? 11.25 times 10 raised power minus 5 Newton. To which axis? To the negative x-axis. The force exerted by Q2 on Q1. Q2 is pushing, I want you to know. They can draw something like this. They can draw something like this. They can say Q1 is at the 2 centimeter, Q1. Q2 is at 4 centimeters, not at original. Q2 is at 4 centimeters, while Q3 is at 6 centimeters. Now, if this is positive, negative, it can be funny, but I've seen students making that mistake. Now, the force exerted by Q2 on Q1 is what? Repulsion, have you?
Yes.
That means Q2